estimate the distribution. So now we have worked with sample estimators, and now I just want to give you a better understanding of why this approach works so well in practice. Because if we have a large enough sample, the sample gonna be pretty much an exact copy of what we expect in the population. Because of course, if we draw everything that can happen, of course the sample is gonna be the same thing as the population. But in practice, we usually can't ask everyone in the population, which means that we have a smaller sample. But I just want to show you an example, and hopefully you're gonna get a better appreciation of why sample estimators work so well. So what I want to do is to revisit the die once again. So we have a 6-sided die. Each outcome is equally likely. We have 6 states of the world representing the outcomes 1, 2, 3, 4, 5, and 6. The only thing I want to do now is that I want to roll this die and then note down each observation. All right? So for example, if I roll the die and I observe a 3, I just put in 3. So now we have one observation of number 3. We roll the die another time, we got another 3, we put it into our figure. We roll it another time, we got a 2, we just put it into the figure. And then we start to continue doing this. We just roll the die, and every time we roll it, we just put the value, the observation, into our figure. And when we do this over and over again, we're gonna note that some kind of pattern gonna emerge here. So first of all, we know that we are pulling from a uniform distribution, which means that we expect to observe the same number of outcomes of each possible outcome. So in this case, we would have expected to observe 5 of each outcome. But due to the random nature of the sampling, we have observed too few 2s, 4s, and 6s, and too many 3s and 5s. But this is just expected. I mean, we are pulling randomly from a die roll. So we just roll the die and then we just note down. Of course, we're not going to get exactly what we expect. We're going to observe deviations. Let's continue just rolling the die, continue noting down. Every time we roll it, we just note down the observation. So when we hit 120, we would have expected to see 20 of each. But now we see that we have gotten too few 2s and too few 5s and too many 3, 4s and 6s and 1s, all right? So let's continue doing this. And what's gonna be fascinating now is that since this sample is being pulled from a population, the sample distribution itself should represent the underlying distribution. So we know that this should be a uniform distribution, meaning that each outcome should be equally likely. And now when we have rolled the die 1000 times, look how closely this distribution resembles a uniform distribution. You can almost see the sample distribution and you can almost feel, just by looking at the sample distribution, that this is pulled from a uniform distribution, which means that each outcome is equally likely. And here, if we continued pulling more and more samples here, so we go to 100,000 die rolls, 1 million dice rolls, we should get closer and closer to the true underlying distribution. And this is the basic idea of using sample estimates. If you have a large enough sample, the sample should pretty much be a one-to-one copy of the true underlying population distribution. And that's why we can use sample estimators to get real estimates of the true underlying value, of the true distribution of the population. But we need a large sample. So if we have a large enough sample, then we can use the sample to not just estimate the mean and the variance, but we should be able to use the sample to even tell us something about the distribution of the population. Next, I want to show you the most important results in the whole of statistics, the central limit theorem.